In physics, thermal conductivity is the property of a material to conduct heat. It is evaluated primarily in terms of Fourier's law for heat conduction. Heat transfer occurs at a lower rate across materials of low thermal conductivity than across materials of high thermal conductivity. Correspondingly, materials of high thermal conductivity are widely used in heat sink applications, and materials of low thermal conductivity are used as thermal insulation. The thermal conductivity of a material may depend on temperature. The reciprocal of thermal conductivity is called thermal resistivity. Thermal conductivity is actually a tensor, which means it is possible to have different values in different directions. See #thermal anisotropy below. Units of thermal conductivity. In SI units, thermal conductivity is measured in watts per meter Kelvin. The dimension of thermal conductivity is m1L1T-3θ-1. These variables are mass, length, time, and temperature. In imperial units, thermal conductivity is measured in BTU. Other units which are closely related to the thermal conductivity are in common use in the construction and textile industries. The construction industry makes use of units such as the R value and the U value. Although related to the thermal conductivity of a material used in an insulation product, R and U values are dependent on the thickness of the product. Likewise, the textile industry has several units including the TOG and the CLO, which express thermal resistance of a material in a way analogous to the R values used in the construction industry. Measurement. There are a number of ways to measure thermal conductivity. Each of these is suitable for a limited range of materials, depending on the thermal properties and the medium temperature. There is a distinction between steady-state and transient techniques. In general, steady-state techniques are useful when the temperature of the material does not change with time. This makes the signal analysis straightforward. The disadvantage is that a well-engineered experimental setup is usually needed. The divided bar is the most common device used for consolidated rock solids. Experimental values. Thermal conductivity is important in material science, research, electronics, building insulation and related fields, especially where high operating temperatures are achieved. Several materials are shown in the list of thermal conductivities. These should be considered approximate due to the uncertainties related to material definitions. High energy generation rates within electronics or turbines require the use of materials with high thermal conductivity such as copper, aluminium, and silver. On the other hand, materials with low thermal conductance, such as polystyrene and alumina, are used in building construction or in furnaces in an effort to slow the flow of heat, i.e., for insulation purposes. Influencing factors. Temperature. The effect of temperature on thermal conductivity is different for metals and nonmetals. In metals, conductivity is primarily due to free electrons. Following the Wiedemann-Franz law, thermal conductivity of metals is approximately proportional to the absolute temperature times electrical conductivity. In pure metals, the electrical conductivity decreases with increasing temperature, and thus the product of the two, the thermal conductivity, stays approximately constant. In alloys, the change in electrical conductivity is usually smaller, and thus thermal conductivity increases with temperature, often proportionally to temperature. On the other hand, heat conductivity in nonmetals is mainly due to lattice vibrations. Except for high-quality crystals at low temperatures, the phonon mean free path is not reduced significantly at high temperatures. Thus, the thermal conductivity of nonmetals is approximately constant at high temperatures. At low temperatures well below the Debye temperature, thermal conductivity decreases, as does the heat capacity. chemical phase. When a material undergoes a phase change from solid to liquid or from liquid to gas, the thermal conductivity may change. An example of this would be the change in thermal conductivity that occurs when ice at 0 degrees Celsius melts to form liquid water at 0 degrees Celsius. Thermal anisotropy. Some substances, such as non-cubic crystals, can exhibit different thermal conductivities along different crystal axes, due to differences in phonon coupling along a given crystal axis. Sapphire is a notable example of variable thermal conductivity based on orientation and temperature, with 35 with along the C-axis and 32 with along the A-axis. Wood generally conducts better along the grain than across it. When anisotropy is present, the direction of heat flow may not be exactly the same as the direction of the thermal gradient. Electrical conductivity. In metals, thermal conductivity approximately tracks electrical conductivity according to the Wiedemann-Franz law, as freely moving valence electrons transfer not only electric current but also heat energy. However, the general correlation between electrical and thermal conductance does not hold for other materials, due to the increased importance of phonon carriers for heat in non-metals. Highly electrically conductive silver is less thermally conductive than diamond, which is an electrical insulator, but due to its orderly array of atoms it is conductive of heat via phonons. Magnetic field. The influence of magnetic fields on thermal conductivity is known as the Ricci-Ledig effect. Convection air and other gases are generally good insulators in the absence of convection. Therefore, many insulating materials function simply by having a large number of gas-filled pockets which prevent large-scale convection. Examples of these include expanded and extruded polystyrene and silica aerogel, as well as warm clothes. Natural, biological insulators such as fur and feathers achieve similar effects by dramatically inhibiting convection of air or water near an animal's skin. Light gases, such as hydrogen and helium, typically have high thermal conductivity. Dense gases such as xenon and dichlorodifluoromethane have low thermal conductivity. An exception, sulfur hexafluoride, a dense gas, has a relatively high thermal conductivity due to its high heat capacity. Argon, a gas denser than air, is often used in insulated glazing to improve their insulation characteristics.